Moving on to Chapter 8. Chapter 8 is going to focus on acids and bases. Starting off with acids. Acids are defined as molecular compounds that donate a proton or a hydrogen ion in a chemical reaction. They're going to produce, if you put an acid in water, they're going to produce a hydrogen ion. So my question to you is, why do you think a hydrogen ion can be called a proton? So if you look at your periodic table, and I were to ask you how many protons does hydrogen have, I would hope you would say, okay, the number of protons is given by the atomic number, and the atomic number is above the symbol on the periodic table. So for hydrogen, there is just a number 1 above its symbol. So that means there's 1 proton. To be a neutral atom of hydrogen, there would also be 1 electron out here. Okay, but I'm not talking about a neutral atom. I am talking about a hydrogen ion. So it has lost this electron. So if you take an electron off of a hydrogen atom, all you're left with is a proton. So that's why you can call a hydrogen ion a proton. So some properties of acids. Acids have a sour taste. I think we're familiar with this if you have like your citric fruits. So citric acid, like your lemons and your limes and things like that. Acids sometimes sting if you get them on you. They turn blue litmus paper pink. So if I'm in a laboratory and I'm wondering if my solution in my beaker is an acid or not, what I'm going to do is I'm going to grab a piece of blue litmus paper and dip it into the acid, and if it turns pink, that's proof that the solution I have is acidic. Another property of an acid is it neutralizes bases. Here are some common acids. Hydrochloric acid is used for cleaning masonry. Sulfuric acid is battery acid. Nitric acid is used for making explosives. Here is acetic acid, which is found in vinegar. And phosphoric acid is found in a lot of your soda pops. If something I want you to notice real quick about these acids while I have them here. Most of them, so ignore acetic acid here. Most of these acids here are all starting with an H. Okay, so inorganic acids are going to have their H's written first. What's special about acetic acid is it is a organic acid. So when we get to chapter 10, we're going to switch from being in inorganic chemistry to organic chemistry, and I'm going to teach you about organic acids, and they're going to look very similar to acetic acid. So most of your acids, by definition, an acid donates its hydrogen ion. It's the first hydrogen ion that's going to be lost from these inorganic acids. If I give you an organic acid, it's going to be the last hydrogen that's donated in a reaction with an acid. So I want you to memorize acetic acid, and I want you to memorize HCl is called hydrochloric acid. Those are the 2 acids I expect you to memorize its names. Acetic acid, you sometimes find it written like where they put those 2 oxygens together, so CH3C, and then they just go O2H instead of OOH. Either of these is fine. An inorganic chemist likes to write their molecules as molecular compounds with all of the hydrogens written together and all of the hydrogens written together. So it'd be C2. If I counted up my H's, I have 4 H's and 2 oxygens. So make sure you can recognize all 3 of these formulas as being acetic acid. So most often the hydrogen's written first, and memorize hydrochloric acid and acetic acid. Most of your polyatomic ions are derived from acids after they have donated their hydrogen ion. So if I look at my first one here, acetic acid, it's actually written another way that I didn't write for you on the other side. So here's another way of writing acetic acid. Acetic acid is going to donate this hydrogen ion. So it's written this way. This is a nice way to write acetic acid because you're able to see it's an acid because we've written the hydrogen first. Once it donates this hydrogen ion, it's going to be left with a negative charge because it lost a positive charge. So acetic acid turns into the acetate polyatomic ion. Nitric acid is going to lose its hydrogen ion and become the nitrate ion. Here sulfuric acid turns into sulfate if it loses all of its hydrogens. Carbonic acid, it can lose 1 or 2 hydrogens. So if it loses just 1 hydrogen, it becomes the bicarbonate ion. If it loses both hydrogens, it ends up with a -2 charge, and that's our carbonate ion. Phosphoric acid will turn into phosphate if it loses all of its hydrogens. Bases are defined as compounds that will accept a hydrogen ion in a chemical reaction, or another way to think of a base is it'll produce a hydroxide. So it's important that you realize bases have two different definitions, and you use whichever definition you want depending upon the point you're trying to make. So memorize that the bases donate hydroxide ions when you put them in water, or you can say bases accept a hydrogen ion. Okay, acids donate hydrogen ion, bases accept hydrogen ions. So some properties of bases: they have a bitter or a chalky taste. Some of your herbs, you can have bitter herbs. They feel slippery, so if you get a base on your hand, it's going to start feeling slippery because of the reaction it's having with the proteins in your skin. I sometimes clean my house with soft scrub, and soft scrub has bleach in it, which is a base. And so when I'm done cleaning with soft scrub, sometimes I can feel the slippery feel on my hands. What I usually do, since washing it with soap doesn't take it off, I usually go to my refrigerator and look for something I have that's acidic, because I know, let me go ahead and get down here to this. One of the properties of a base is it'll neutralize acids, like acids neutralize bases. So when I've cleaned with soft scrub, if I get it on my hands and I feel that slimy feel, I usually go and get some soda pop or some lemon juice from my refrigerator and pour it on my hands, and it instantly stops that slippery feel. Another property of a base is it turns red litmus paper blue. So in the lab, you have a choice of either grabbing blue litmus paper or this red litmus paper, which is actually pink. And if it's a basic solution, the pink litmus paper will turn blue as an indication that it's a base. So focusing on some common bases. Bases with the hydroxide polyatomic ion are named as just the hydroxide of the metal. So basically they're named as ionic compounds are named. So to refresh your memory, this is an ionic compound because sodium is a metal and it's a cation. Hydroxide is a non-metal, and so it's going to be an ionic compound. And our rules for naming ionic compounds are: you name the metal, ask yourself if that metal has a variable charge or a fixed charge or a non-fixed charge, because you might need parentheses, and then name your non-metal part, the anion, which is hydroxide. So this one would be potassium hydroxide, barium hydroxide. Down here, iron has a variable charge, so you have to put the Roman numeral in there letting you know what the charge is on the iron. So that would be iron 3 hydroxide. The one that I really want you to memorize is ammonia, because ammonia does not have a hydroxide. I really want you to be quick at seeing if the molecule has an H written first, it's an acid. If your molecule has a metal followed by hydroxide ion, that's a base. Okay, so those should be quick to see. Ammonia, however, is not quick to see because it doesn't have that metal followed by hydroxide. So I want you to memorize ammonia is a base. So most of your common bases can be easily recognized since they're metal hydroxides. The reaction of an acid with a base is called acid-base neutralization reactions. The acid's going to react with the base to neutralize it, and it's going to produce a salt. Now salts are ionic compounds. So it's going to produce an ionic compound, and it's also going to produce water if the base had the hydroxide ion. Okay, so ammonia doesn't have the hydroxide water, so we're not going to expect one of the products to be water. But if you're reacting an acid with a base that has hydroxide, then you're going to expect to get salt and water as your products. So here is a first example. First of all, tell me, is my first compound an acid or a base? And I hope you say it's an acid because it has a hydrogen written first. My second compound here is a base. We know it because it's a metal followed by hydroxide. So this would be the example of an acid-base reaction, because I've got an acid and a base on the left side of my arrow. Acid-base reactions are usually double displacement or double replacement reactions, where the hydrogen, the cation from one of my compounds, will go to the anion of the other one, and then the anion of the first compound will combine with the cation of the other ones. So the hydrogen that's given up by the acid is going to bond to the hydroxide given up by the base, and that's where we get our water. And then you have to put the anion from the acid and the cation from the base together to make your salt. Remember that you always write the metal before the non-metal when you're putting your salt together. Here's a reaction of phosphoric acid with sodium hydroxide. Here we had to balance it because my phosphoric acid had 3 H's to give up, and sodium hydroxide only has 1 hydroxide. So you end up needing 3 of these bases, and that's going to yield 3 waters. My last example is has ammonia in it. It doesn't matter on the left side, on the reactant side, whether you write the base or the acid first. So here's an example where I'm writing my base first and the acid second. So ammonia does not have a hydroxide to give. So what ammonia does, because it's a base, is it's going to, instead of donating a hydroxide ion, it's going to accept a hydrogen ion. So where is it going to get that hydrogen ion? It's going to get it from the acid, which is fine because the acid's willing to donate that hydrogen ion. So this hydrogen ion is going to go land on the ammonia, and it's going to turn into NH4, the ammonium cation, which is then going to stick together with the chloride anion. And so we're going to get the salt ammonium chloride. Okay, so that's the reaction you're going to need to be able to do for acids and bases. What happens if you put an acid or a base in water? So here, the example I have here is acetic acid. If I put that acetic acid in water, well, it's going to do what every good acid does, and it's going to donate its hydrogen ion. Since it's an organic compound, it's that last hydrogen that's lost. Where is that hydrogen going to go? Well, in this case, it's going to go to the water. So the water is going to act as a base, and it's going to accept that hydrogen. So it's going to turn into H3O with the plus sign. So that's where you get the hydronium. The hydroxide, when it lost that hydrogen, then it's going to end up getting a negative charge, and that'll be the acetate ion. So an acid in water, the acid's going to donate its hydrogen to the water, and you're going to get hydronium and the anion of the base, or of the acid, sorry. Hydronium is the polyatomic ion. So this H3O plus, I do want you to memorize, is called hydronium. What happens when I put a base in water? Well, in this particular case, the base is going to accept the hydrogen from the water. So it takes off one of these hydrogens, and it takes it off as a hydrogen ion, so that leaves this as the hydroxide ion. And that hydrogen ion is going to come over here and turn the ammonia into ammonium cation. Okay. Conjugate acid-base pairs. In any acid-base reaction, there's going to be 2 conjugate acid-base pairs. Okay. Each pair is going to be related by the loss or gain of a hydrogen. So let's look at the reaction down here. This is a generic formula that we use for an acid, because I have an H first, and this would be the anion that the hydrogen ion's on. And then a capital B is just the generic variable we use for a base. So here's my acid-base reaction. What's going to happen as I proceed to the right is my acid is going to do like all good acids, and it's going to give up the hydrogen ion, and it's going to turn into just the A minus because it lost the hydrogen ion. So this right here would be 1 acid-base pair. My base is going to do what every good base does, and it's going to accept a hydrogen ion and turn into BH plus. So this would be my other acid-base conjugate pair. Okay. One of your acid-base pairs occurs in the forward direction. So if I were to label these, this is my acid, and once it loses that hydrogen ion, it turns into a base. My base, when it gains a hydrogen ion, is going to turn into an acid. Okay, so an acid-base pair in the forward direction would be this one here. If I go in the reverse direction, my acid is the BH plus turning into B. So just be able to identify your acid-base pairs. So to get the conjugate acid, so if I ask you to write the conjugate acid, you're going to add a hydrogen ion to the conjugate base that I give you. If I ask you to write a conjugate base, I'm going to have to give you the acid, and you're going to remove a hydrogen ion from the acid. So here's a couple examples. It's easy to get these confused, so you'll want to kind of read through these carefully. This is how my brain interprets these, so I'll walk you through how I do these. This A is asking for the conjugate base. So it wants me to write down the base of carbonic, or the bicarbonate ion. So first of all, let's look at the bicarbonate ion. He's special. He has a hydrogen he can donate, so bicarbonate can act as an acid by giving up this hydrogen, or he can act as a base and accept a hydrogen, because the negative charge out here is telling you that it can accept an H+. So what is the bicarbonate ion going to do in this case? Is it going to lose an H or is it going to accept an H? So the clue is in what I'm asking you to write. So I want you to write the conjugate base. That must mean this bicarbonate ion is going to act as an acid if I want you to write the base, the conjugate base of him. So if it's acting as an acid, it's going to lose its H, and its negative charge is going to decrease by 1 because it lost something that's positive. So instead of being a -1, it's going to become a -2. So the answer to this one, A, is going to be 1. What is the conjugate acid of the bicarbonate ion? So now I'm asking for the acid, so the bicarbonate ion must be acting as a base. I personally think it's helpful to take the time and label the molecule I give you as, is it going to be an acid or a base? Bases are going to accept a hydrogen ion. So instead of having 1 hydrogen, we're going to make it 2, and it's going to add a plus sign to this -1, so the negative sign is going to disappear. So the answer to B is 3. C wants you to write the conjugate base of water. So if I want the conjugate base, then the water must be acting as an acid. It's going to lose its H plus and leave us with 1, the hydroxide ion. If I want the conjugate acid of water, then water is going to be acting as a base, which means it's going to accept a hydrogen ion, and it's going to end up looking like hydronium. Notice that water can act as either an acid or a base depending upon what it's reacting with. So in this example here, what is water reacting with? Well, I've added a base to the water. So if I add a base to the water is going to act as an acid. The base will accept the hydrogen ion from the water, and the water will then turn into hydroxide. If I mix an acid in water, so here's my acid, this time the water is going to act as a base. So the acid's going to donate a hydrogen, that base is going to accept it and turn into hydronium. So water can either be an acid or a base depending upon what you're reacting it with. There was something I wanted to point out here and I've forgotten. So if water can act as an acid or a base, can they react with each other? And the answer is yes, water can react with each other. What happens is a hydrogen is transferred from one water molecule to another. One of the water molecules acts as the acid while the other one acts as a base. So here what happens is you have 2 water molecules that'll bump into each other. One of them is going to donate its hydrogen to the other one. So if this one right here loses a hydrogen ion, it's going to turn into hydroxide. And then this one that gains it's going to turn into hydronium, or vice versa. It doesn't matter which way I've drawn the arrow. One water molecule donates a hydrogen ion, one accepts the hydrogen ion. So let's see which way I have it in this picture. In this picture, you're looking at the Lewis structures. I can't find my arrow. This water molecule, it looks like it's going to take a hydrogen ion from this water molecule. So this one is going to turn into hydronium with its plus charge. And the other water molecule that lost a hydrogen ion is going to be hydroxide with the minus sign. It turns out that in pure water, if you've purified water and you're about room temperature, only one molecule, every one water molecule in 550 million is going to go through this ionization process. So most of your water molecules, if you have a glass of water, most of them are going to stay just as neutral H2O. But 1 in every 550 million are going to bump into another water molecule and turn into hydronium and hydroxide. It turns out that if you measure the concentration of hydronium and hydroxide, it has a concentration of 1 × 10⁻⁷ molarity. So that's a very small number. So there's not very many hydronium and hydroxides floating around in your glass of water. Notice that these numbers are the same. That should make sense, because from the previous slide, when 2 water molecules bump into each other, you get 1 hydronium and 1 hydroxide. So their concentrations are equal to each other. My question to you is, will pure water conduct electricity? And I hope you can see that this is such a small concentration of hydronium and hydroxide that there's just no way that that's going to carry a current. Because remember, you have to have a lot of charge floating around in your solution to make the current to conduct electricity. So pure water should not be able to conduct electricity. However, most of the time when you have water, it's not very pure. It's going to have minerals in it, it's going to have some ions from the chlorination process, things like that. So the ionization of water, that's what we've been talking about with when they bump into each other and make the hydronium ion and the hydroxide ion. In an aqueous solution, aqueous means a water solution, of the hydronium multiplied by, so times, hydronium concentration times the hydroxide concentration is always a constant number. We give that constant, this Kw, which is the ionization constant for water. You don't need to know that. What you do need to know is that when you multiply the hydronium times the hydroxide, that is always going to equal 1 times 10 to the negative 14. So this is a formula that I have for you on your information sheet. So you're going to want to be able to use that, where I might give you the concentration of hydronium and ask you for hydroxide, or give you hydroxide concentration and ask you for the hydronium concentration. So you need to know that to go get your formula from the information sheet and solve for what I'm asking you for. The brackets indicate that the concentration needs to be in molarity. So these brackets here is saying, these brackets here are saying the hydronium concentration in molarity, the capital M, hydroxide concentration in molarity. If we add acid and the hydronium concentration goes up, so hopefully you can see that. Adding acid to water, the acid is going to lose its hydrogen ion. The hydrogen ion is going to land on a water molecule and make hydronium. So in an acidic solution, you increase the amount of hydronium. So since the amount of the product of hydronium and hydroxide always has to equal a constant number, if one of them goes up, the other one has to go down. It's an inverse relationship. Okay, so if acid is added and the hydronium goes up, then the hydroxide concentration must go down, so their product stays 1 times 10 to the negative 14. It turns out that if the hydronium concentration is equal to the hydroxide concentration, then it's going to be a neutral reaction, not acidic or basic. However, if the hydronium concentration is greater than hydroxide, then it's going to be an acidic solution. And if the hydronium concentration is less than hydroxide, that's going to lead us to a basic solution. Basic solutions are also called alkaline solutions. So make sure you get that memorized. So here's a graph just going over exactly what I just said. If we look at the y-axis, right here is a concentration of 1 times 10 to the negative 7. So remember that that is your neutral state. If the hydronium and the hydroxide are both 1 times 10 to the negative 7, then that is going to lead us to a neutral solution. Hydronium and hydroxide equal to each other. If I increase the amount of hydronium, hopefully you can see that means we're talking about an acidic solution here, because I have a lot of hydronium floating around because my acid gave the water the H+. If I increase the hydronium, I have to decrease the hydroxide, so that whatever number the hydronium is times whatever number the hydroxide is here, it's going to end up equaling 1 times 10 to the negative 14. Over here in a basic solution, that means we have a lot of hydroxide, because bases donate hydroxides, which means we have to lower the amount of hydronium. So this is the scenario we have for a basic solution. Dealing with acids and bases, we often talk about the pH scale. The pH is a convenient measure of the hydronium ion concentration. Brackets are used once again to indicate the molarity. So here is the formula we use to calculate the pH. pH is equal to the negative, so this is a negative symbol, negative log of whatever the hydronium concentration is. So make sure you can do this calculation on your calculator. So make sure you find your log button, and you're just going to type in negative log and then whatever the hydronium concentration I give you. Some calculators you have to do the log first and then take the negative. So figure out your calculator. This equation I give to you on your information sheet. For simplicity, sometimes the bracket hydrogen ion is used instead of the hydronium. So a chemist knows that the acid is giving up a hydrogen ion, which is going to land on water to make hydronium ion. So the concentrations of the H+ is equal to the hydronium. So we're often lazy, and instead of writing pH equals negative log hydronium, we often just write pH equals negative log of the hydrogen ion. But you need to know that really this is just a symbol for the hydronium. Okay, so what I've put the square around here is what is on your information sheet. So if I ask you for the pH, go get that formula. The pH of a solution is used to indicate the acidity of a solution. It has values that range between 0 and 14. The pH is acidic if the value is less than 7, neutral if the pH is 7, and it's basic if it's greater than 7. So you want to have that memorized. The pH scale goes from 0 to 14. 7 is neutral, less than 7 is acidic, and greater than 7 is basic. Here is a picture showing some household solutions and their pH values. So we'll go through this. It's kind of fun. I don't necessarily like how this picture has the arrow going up to 0, because I sometimes get students, it took me a long time to figure this out. Students would say to me, oh, the pH is going up, when really the number was getting smaller. If you say to me the pH is going up, my brain thinks that it's going closer to 14. So going up in pH is getting a higher number. And it took me a while to figure out that what they meant was it was going up because this picture is showing up, but notice the numbers are going down. Okay, so if the pH goes down, you're getting closer to 0. So hydrochloric acid has a pH of 1. I'm sorry, I said that wrong. A 1 molar solution of HCl. So if I have hydrochloric acid with a concentration of 1 molar, that's going to be a pH of 0. Gastric juices have a pH of 1.6. So the lemon juice is 2.2, so lemon is pretty acidic. Vinegar is fairly acidic too with the 2.8. Your carbonated beverages have a pH of 3. Orange juice, I think most of us are familiar with that being acidic at 3.5. Apple juice, most students don't realize how acidic apple juice is, 3.8. Tomato juice, or tomatoes, is acidic. Coffee is acidic. Bread, here's potatoes. Urine has a pH of 6.0, so slightly acidic. Milk is very slightly acidic too with a 6.4. So the closer you get to 7, you're getting closer to neutral, so it's not super strongly acidic. Here's pure water with a pH of 7. Blood has a pH of 7.4, so slightly acidic or slightly basic. Blood is slightly basic. Detergents are basic. Seawater, milk of magnesia has a pH of 10.7, so anything bigger than 7 is a base. This should make sense because people take milk of magnesia when they have an acidic stomach, and so the milk of magnesia will neutralize some of the extra acid in your stomach. Ammonia, we've already talked about, is a base. Bleach is a strong base. Yes, 1 molar sodium hydroxide has a pH of 14. So Drano is mainly sodium hydroxide, so that's a very strong base. Here is a picture that's just relating everything I've told you about. So the hydroxide going up, hydronium better go down, the pH and things like that. So let's go ahead and take some time looking at this for just a second. Let's start off with our neutral position. If the pH is 7, we are at neutral, and the hydronium concentration equals the hydroxide concentration. It's good to kind of get this, oops, my pen is freaking out. It's good to get this 10 to the negative 7 memorized, because that is your neutral point. If I decrease my pH, so my pH is getting a smaller number, meaning I'm getting closer to 0, that means I'm getting more acidic. So what should be happening to my hydronium concentration? If I'm getting more acidic, the hydronium concentration better be increasing. And that's what's happening. It's going from 10 to the negative 7, 10 to the negative 6, 10 to the negative 5. I'm hoping you can see that these numbers are actually becoming bigger numbers because the exponent is less negative. If my hydronium numbers are getting bigger, what's happening to my hydroxide numbers? They are getting smaller because hydronium and hydroxide are inversely related. So in an acidic solution, because all of these here are acidic, in acidic solutions you have your hydronium concentration larger than 10 to the negative 7, your hydroxide concentration is lower than 10 to the negative 7. And then the opposite is true for the bases. So any solution with the hydronium greater than 10 to the negative 7 is going to be acidic. If your hydroxide concentration is greater than 10 to the negative 7, you're basic. So that's kind of worth getting down. It makes doing some of these questions easier. This is just a summary slide of some of the equations that I've given you so far. These first two are on your information sheet. So if I ask you to solve for the pH, you're going to get this equation. If I want either the hydronium concentration and I give you hydroxide, or I give you hydroxide and I want hydronium, you're going to get this equation. Okay. These I do not give you on your information sheet, so you just have to flat out memorize those relationships. So here's a learning check. Identify each solution as either being acidic, basic, or neutral. So if we look at A, besides the fact you're going to memorize hydrochloric acid as an acid, so it's going to be acidic, you're going to know it's acidic because the pH is less than 7. So acidic is the number 1, so we'll put that there. Pancreatic fluid has a hydronium concentration of 10 to the negative 8. Now here's where you have to think about that neutral point of 10 to the negative 7. Is 10 to the negative 8 bigger or smaller than 10 to the negative 7? So we're going to run here. 10 to the negative 7. And hopefully you're telling me that 10 to the negative 8 is smaller than 10 to the negative 7 because the exponent is more negative. So if the hydronium is less than that neutral point, then that must mean I have less hydronium, so I have more hydroxide. And that is one of our definitions of a base. So I'm going to give this a 2 because my hydronium is less than neutral, so hydroxide must be bigger than neutral. pH of 3 is in the acidic range, so that's a 1. pH of 7 is neutral, so that's 3. Hydroxide concentration is 10 to the negative 7, so or 10 to the negative 10. So how does that relate to 10 to the negative 7? Well, 10 to the negative 10 is less than 10 to the negative 7, so that means I do not have much hydroxide. So if my hydroxide is low, that must mean my hydronium's high, and that is a situation that is acidic. That would be a 1. Here they're giving me hydronium concentration, which is less than 10 to the negative 7. So that means I do not have much hydronium floating around, so that would be a base. Here's a learning check. What is the pH of a solution if the hydronium concentration is 4.5 times 10 to the negative 3? So this particular question is asking me for pH. If ever I'm asking you for pH, you're going to go get the formula from your information sheet. That says pH is equal to negative log of your hydronium concentration, but it shortens it to the hydrogen ion concentration. So we just have to plug everything in. We're going to say the pH equals negative log of, and we're going to plug the hydronium concentration in here, 4.5 times 10 to the negative 3, and that is going to equal 2.3. Notice pH does not have any units on it, so just to 2.3. What is the hydroxide concentration of the same solution? Now the only formula you have to get the hydroxide concentration is the one that says hydronium concentration times your hydroxide concentration equals 10 to the negative 14. So we are going to plug our hydronium concentration in here and solve for the hydroxide. I actually like to solve for my missing variable first before I plug my numbers in. So if I divide both sides by the hydrogen ion concentration, and now I'm going to plug this stuff in. So 10 to the negative 14 divided by the hydronium concentration, 4.5 times 10 to the negative 3. And I type that in my calculator. Now remember, just to refresh your memory here, if you're not using your exponent key, you better make sure you put parentheses around your denominator, or you're going to get the wrong number. So when you type this in, you end up with 2.2 times 10 to the negative 12. Notice the unit is molarity. That's because we're solving for brackets here, the concentration of hydroxide concentration. Which is larger at the pH calculated? So we calculated a pH of 2.3, which is acidic. So which is larger, the hydronium concentration or the hydroxide concentration? Well, here's hydronium, 4.5 times 10 to the negative 3. Hydroxide is 2.2 times 10 to the negative 12. So which one of those is bigger? And you are hopefully going to tell me that the answer to this question is the hydronium concentration is bigger. Is this what you would expect? Well, I hope so, because if we have a pH less than 7, we better have a higher hydronium concentration and a lower hydroxide concentration. And this just mathematically proves that relationship. Testing for pH. There's several ways you can test for the pH of a solution. If you are working in a laboratory, you're just going to use a pH meter, because that's going to be your quickest way. You just put the probe in the solution you're looking for, and your pH meter is going to just digitally spit out whatever the pH is. So that's the quick way of doing it. If you happen to have a jacuzzi or a pool at your house, you might be familiar with these pH strips. So you take out one of the pH strips and you dip it in your solution, and you pull it out, and it's going to change a particular color. And you could compare that color to the color guide that they give you to help you determine what the pH is. Another way of determining the pH is indicators that have a specific color change at different pH values. So there are particular like plants and compounds in nature that have what we call a pH indicator. So pH indicators are just molecules that can change color when the pH changes. Purple cabbage is an example of that. We're actually going to do this in lab, where we take purple cabbage and we're going to boil it, and we're going to take the cabbage juice, and that cabbage juice is going to contain a molecule in it that is a pH indicator, because it changes colors depending upon the pH. So depending upon the color, we're going to, I don't want to spoil the lab for you, so you're going to use cabbage juice to help determine the pH of some household solutions.